Hello everyone! Today I would like to present a video called Key Mathematical Tools We Require for Modeling Physical Reality. In this video we will develop a few of the tools of mathematics that we really need for describing the behavior of the physical world, and in this case especially for describing quantum mechanical waves as they travel. So what we hope to accomplish in this video are four things. Specifically, we will develop a definition of the exponential function that does what we need it to do. And secondly, we'll solve for this exponential function for the condition where the function is equal to the slope of the function at any points. And that's a very, very specific case that proves to be enormously useful, especially when you're trying to solve derivatives. And it's just an amazing thing. And then we'll discuss item number 3, the meaning of the operator J. And I want to make it so clear that we can form a picture of it that's easy to remember, a geometrical view of this operator. And then step number 4, we want to show geometrically the meaning of E, a special number. You have E to the J, so that you can know it in your bones. And you'll find out through this presentation what's so very special about the number E. In fact, we're going to derive it to do a specific service for us, a very, very, very powerful service when it comes to modeling, and also for solving so many arithmetic problems. So let's continue. Let's get into it now. So I looked in many physics books and in a math encyclopedia and Schwamm's outline series, and went on the internet and looked at Wikipedia and those sorts of things. And I found that the usual definition for an exponential function was something like this up here. F of x is equal to b to the power x. Okay, now that seems pretty good. And a lot of the people I know have been exposed to that definition. But when I ask them, well then what's f of 0 then? You know, b to the 0, what is that? And let's see what we got. They give me an answer typically that doesn't help much. It's not really correct, and makes me think that there's something wrong in the way that people interpret a definition. And I would even go so far as to say that, you know, you want to make a definition that leads people to the right answer and doesn't lead them to the wrong answer. So in my mind, it should be possible to make a better definition of the exponential function so that the majority of the people would give the right answer, which we're going to derive, by the way. So let's look at this. We'll give an example here where x equals 3. So try f of 3, and that's going to be equal to b cubed, or b to the third power, and that's going to be equal to b times b times b. And so far so good. You know, the definition seems to be working fine. And then we say for x equals 1, well, f of 1 is equal to b to the first power. And, you know, like if you think of 10 as 10 to the 1, you know, 10 to the first power, that's just 10. So that's going to be equal to b. b to the 1 is going to be equal to b. And so far, that's a good answer. Bravo. So now we continue on and we say, okay, for x equals 0, what's f of 0? And you think, well, that's going to be b to the 0. Now, you know, b to the 1 is b, b to the 2 is b times b, b to the 3 is b times b times b. So b to the 0, you think, that's going to be nothing, like no b's at all. So that's going to be equal to 0. You know, it sounds so great. But no, it's not okay. It's not the answer we need, okay? And my view of mathematics is that it's built to model whatever we're trying to model. And let's say we're trying to model physical reality, then it has to give the real answers. And that's not the answer we need here. So the definition seems very logical, but in many people, it produces the wrong result in the way they think about things. And when a logical extrapolation from a definition produces undesirable results, then I think perhaps the definition itself might have some problems built in. So let's make a new definition of the exponential function. All right. So here it is. Wow, we got here so fast. New definition up here top. New definition of exponential function. So I'm going to do it in words first. The exponential series is a multiplicative series in which the second term is the base, which is just a number that remains constant through the entire series. For example, the third term, we multiply the second term by the base again, okay? And for the fourth term, we multiply the third term by the base again. And we continue all the way up to infinity if we like. So in this definition, I've given you also a bit of a formula of how to construct the exponential series. But notice I left out the first term, which is b to the 0, because having defined the series from b to the 1, b to 2, b to 3, we have more than enough to derive what b to the 0 has to be, okay? So yeah, and I was scooped by one derivation of this that went on for a couple of pages, and I was pretty impressed with the derivation until I thought about it just last couple of days, and I realized, oh my God, it's so evident when you get this new definition. It just kind of jumps out at you. So here I'm going to derive it b to the 0. Oh, I should tell you first, notice b to the 0 is right at the beginning. It's the first term. And then you can go b to the 1. And then the next term is b to the 2, which is b to the 1 times b, right? And then b to the 3, which is b to the 2 times b. And you can continue that all the way up to positive infinity. But look here, I'll use my arrow here, b to the 0. You can go the opposite way. If you go to the right, it's going to the next one's b to the 1. If you go to the left, it's b to the negative 1. And what that means is 1 over b, right? It's like the inverse. And then b to the negative 2 is 1 over b squared, right? And b to the negative 3 is 1 over b cubed. And you can continue that all the way down to b to the minus infinity, which is 1 over b to the infinity. All right. So here we're going to derive what the value for b to the 0 from what our definition of the exponential function, the new definition. So I asked the question, what is the value of b to the 0? Okay, so let's think about this. In the exponential series, when you multiply the two terms, the exponents add, okay? So b to the 0 times b to the 1 is equal to the b to the 0 plus 1. Here I'm adding the exponents, all right? So great, that's good now. Now I can divide both sides of this expression here that I'm running the red arrow over. I can divide both sides of that expression by b to the 1, okay? So it cancels out on the left-hand side of this expression. You just get b to the 0. And on the right-hand side, you get b to the 0 plus 1 divided by b to the 1. Now, b to the 0 plus 1, what's 0 plus 1? Have you lost that? Do you remember? B to the 0 plus 1 is equal to 1, right? So b to the 0 plus 1, it's b to the 1, right? So I replace in the line above here, b to the 0 plus 1, I replace that with b to the 1, right there, all right? And then when I divide by both sides by b to the 1, I get b to the 0, and I get b to the 0 1 plus 1 over b to the 1, but that's just b to the 1 over b to the 1, which equals to 1. So I get b to the 0, way over in the left-hand side, and then I get is equal to 1 on the right-hand side. So right there, I remember I said it's so quick that you don't blink, you'll miss it. There it is. So simple. So we know that b to the, I'm going to, in the yellow box below here, b to the 0 is equal to 1. We just derived that. And I take that and I stick it into this the series that we defined above here. And where it says b to the 0, we know what that is. It's equal to 1. So here's the new definition of the exponential function, the exponential series. And it starts at 1 in the middle, and then it goes plus b to the 1, plus b to the 2, plus b to the 3, blah, blah, blah. This is the series. And on the other side, of course, b to the -1, b to the -2, b to the -3. Okay, so we basically derived that. Well, first of all, we defined a new function, more specifically. And then we used that to be able to determine what the value of b to the 0 is. We proved it. And we're going to need that later. And I think I've said this already, but this is going to prove to be very helpful in a language that we're going to use to describe quantum mechanics. And if you understand that language deeply, which I'm going to help you with here, then you can really understand quantum mechanics very easily, and it'll feel natural rather than foreign. So now, as I like to put the reminders back, what are we here to accomplish today? And I said specifically, we will develop a definition of the exponential function that does what we need it to do. Okay, so I put a check mark there because we did that, right? So what's next? Number 2, solve for this exponential function so that f of x is equal to the slope of f of x. All right, so we're going to do that. I'll talk about it a bit more. And so that's all we need to know right at the moment. What we're going to do next, which is solve for the exponential function for the specific case where f of x is equal to the slope of f of x. So it's like a car going up a hill. It goes up 10 feet and it goes over 10 feet. So it's 10 feet high. Oh wait, that's not quite right. That would be an angle of 45 degrees. But you want the slope. You want the slope. Let's say the car goes up on the hill 10 feet. Well, then the slope is equal to 10. And if the car goes up to 15 feet, then the slope is 15. And you might want to think of getting out of that car because it's going to fall over and land on the ground. That's a pretty steep slope. So anyway, it gives you the idea. Now let's continue on to the next thing, which was solve for this exponential function. So f of x equals the slope of f of x. Now notice, this is mathematics, and a lot of people, including myself, you have to be kind of coerced to stay with it because I don't know, it can be a little dry at times. Now, so here, but you get a tremendous bonus when you go through it. So let me just encourage you because we're almost halfway through. We've got the first one done, and you hardly notice it, and now we're already into the second one. So we're going to solve for that. So let's do it. So here I say on the top, I'll get my red arrow again. The slope is the change in the height of the point on the line over a small change in the horizontal axes divided by the change in the horizontal axes. So if y equals f of x, then the slope is given by the following process, okay? Remember, this is a specific case, and we're going to solve to find out what is needed to make that case come true. So here we have the slope, the change in the height of the f of x divided by the change in the horizontal, dx, okay? So here we have, and by this is known as a derivative, and it's also known in common terms as the slope. Now, the slope, if you have a curve and you want to find the slope at a point, you introduce a little perturbation. You go along the line and change the height a little bit, and then see how far it's changed on the base, x. This little change in x, which we can call delta x, produces a change in y, which is f of x plus f of delta x, right? So that gives you the slight bit of height, and then you subtract from that the height that you had before, and you get the change in the height. So through that little expression, you get the change in the height with the change in the base, along the bottom. Like a car, you go in a little bit and it goes up the hill more, and you take the change in the height over the change in the horizontal direction, and you get the slope. So this is very simple. I like to call it sandbox definition, because a young person could, if you ask them the right questions, they would come up with this. Talk about cars going up a hill and that sort of thing. So anyway, enough said. Here's the expression right here. Now, in the case of an exponential function such as b to the x or b to the 3, the differential slope is expressed as dy by dx is equal to b to this exponent that has been increased by delta x, okay? That's the function b to the x. So a little bit more of an x will give you b to the x plus delta x, okay? That's the exponential function there. And what you had before was just b to the x. So you subtract that. Now you get the change in the height. And then down here you have delta x. Oh, that's the change in the base. That is the slope. It's so much a slope. Okay, and then you take that as delta x gets smaller and smaller and smaller. And that gives you the value dy by dx. And then, so we have that. Now we want this to find the specific value b. I'm going to make that b red so it sticks out. Yeah. There we go. And the specific value b for which f of x is equal to the slope. The value of the function is equal to the slope. Okay. So when you have that, then you can set f of x is equal to dy by dx. I just said it again. I say it so many times it might sink in better. But it helps to point it out. F of x, the function, is equal to its slope. And then I write this down again. We've already gone through that. That's the canonical, which just means standard definition of slope. And it's very, very intuitively satisfying as well. We already went over it. So let's move on. Okay. So starting here, y equals f of x. And that's the function. And it's equal to its slope. So we get this, okay? As delta x goes to 0. All right, so for x equals 0, b to the 0 is equal to 1. We proved that above. Yes, we did. B to the 0 is equal to 1. Remember, we derived the new definition, and then we went through and used that to prove we got the series b1, b2, b3, where b1 is the second term, and we used that to derive the value of the first term. Anyway, so at x equals 0, f of 0 is equal to b to the 0 is equal to 1. Okay. Now dy by dx, where for the b, where f of x is equal to the slope, the function is equal to the slope, then it's going to be b to the x plus delta x minus b to the x, and that's because we know x is equal to 0 in this case. Then it's going to be equal to b to the 0 plus delta x minus b to the 0 over delta x. Now we know that b to the 0 is equal to 1, so we put that in there. And we know that delta x equals, b to the 0 is 1 here, so 1, but it's 1 plus delta x. So it's just b to the delta x minus 1. So f of x equals 1 equals b to the delta x minus 1 divided by delta x as x goes to 0. That then is the expression that we have to solve in order to have the function is equal to its derivative. You need to have this expression solved. So to produce an exponential function that is equal to its derivative, we must solve the expression above for b. Notice here, We know that delta x is going to get smaller and smaller and smaller. We know that 1 is going to stay a constant. And we know that the value 1 over here, it doesn't change, so it's a constant. And here's delta x again, which is getting smaller and smaller and smaller. This b value is kind of the variable that needs to be defined in order to make that true. So the expression above for b, and I write it again, as delta x go to 0, is basically the expression f of x is equal to dy by dx at x equals 0. So we're going to solve for that. So we take, when we solve for this expression, which we just derived, we get the that f of x is equal to dy by dx. That is the solution. So one way to solve this, and I like this because it turns out that the solution value, we'll go back, I want to show you, that the value for b that makes this all true turns out to be an irrational number, which just means it goes on and on and on. And we find that by, like, I put this into an Excel spreadsheet, and then I just made delta x smaller and smaller, and corrected b to make this be as true as possible. For example, I can put this expression in, then subtract 1, and then make the what's left change b and see which direction makes it smaller and smaller and smaller. And then if then that you can use that process to solve for b. And when you do that, you get this number here. And I only took it so many decibels, but just shy of 3. It's 2.718282845945945. Anyway, it goes on and on. But it's a number just shy of 3. And so here's the result. 1 is equal to 2.7182 blah 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 blah, and continues on and on and on. And that number, let me see, I gotta continue on this presentation. That number, it turns out, it's so special because it's the exponential function where the base is chosen to have that number, be that number. And for that particular number, the derivative of the function is equal to the value of the function at that point. And that's an amazingly useful tool. So now I want to geometricize it. I want to make it into an image that helps you both understand it and remember it. And when you're lying down on the couch or whatever, thinking about something, you can pull up that image and see the whole thing all at once, rather than have to go through line by line with a lot of notational issues and referring to other proofs, that to the traditional algebraic type of proving things. You don't get to really see what's going on necessarily now. And I like to say it's like the difference between hearing music and looking at a sheet of music and seeing the score. I think being able to look at the music and see the score is very, very good. But I also want to hear the music. Like people, they typically don't get a book of music and look at it and get a big thrill. The thrill of music is to hear it, right? Well, I think a lot of the thrill of mathematics is to be able to see it. Okay, so here we go. I'm going to show. Here we have e, that number that we just derived, and for that, f of x is equal to e to the x. Remember, it's an exponential function, so of the base e that we just discovered what the number e is. E doesn't change. It's a number. It's just a number. And it happens to be that number I just talked about above. Let's get my arrow working here. This number. And e to the x then is equal to d, the derivative of e to the x over dx. That's another just way of saying the slope. The function is equal to slope. It's like magic. And we know that we've proven before. I lost my arrow. I've got to get it back. There we go. Whoop. Okay, I got you. Let's do this. There we go. Now I got it. We we proved before that the base to the power 0 doesn't depend on the value of the base. It's equal to 1. It's equal to 1. E to the 0 is equal to 1. So I draw that on a Cartesian plane, and it's equal to 1, so it's a real number. Not too fond of that expression, but you can draw it as a direction. It's going in the positive number direction, 1. And I do a circle around this because I have a foreknowledge of where we're going with this, but you could just as easily take the circle away at this point, but not later on. So at this point, you might wonder, oh, where's that guy going? So I like to come back again and see where we've been. Specifically, we developed a definition of the exponential function that does what we need to do, and we used it to derive the value of a base to the power 0, right? And then we solve for this function. We solve for the exponential function so that the f of x, the function, is at a particular value is equal to the slope of f of x. The function is equal to its slope. And we found out what base allows that to happen, okay? And it's the base e, which is just a number. It happens to be an irrational number, which means it goes on and on and on. So we did that, and we found out what e was, okay? Now the third thing, and I haven't changed these from when we introduced this presentation. The third thing is we want to discuss the meaning of the operator J. And I promise you're going to like this. And let me also say at this point, because we're doing mathematics and got to keep ourselves awake here. Look, we're half the way through this thing already. You know, it's going quick. And so just hang in. You will be immensely rewarded if you just stick through this. I promise you. Okay, so let's go and do number 3 here. So now, the operator J, what is that? Now when I was a student in school, I'm still a student, but a student of life. Actually, I probably learn more every day now, much more than ever, and I don't intend to stop that. But when I was a kid, I was introduced to the number J as being the square root of -1. And I didn't like that, because if I take, to me at the time, there's only a square root. It's going to be either 1 or, positive 1 or -1. And then I go, okay, well then if the square root of -1 is J, then I should be able to figure out what J is. So the square root of -1, so we go -1. What do I multiply by itself to equal -1? I go -1 times -1, that's positive 1. And positive 1 times positive 1 is equal to positive 1. So I can't get to -1. It's like an island that's not even connected to the planet, right? So, yeah, I didn't like that too much. Or at least I was hungry for something, an explanation. It turns out it really doesn't have any meaning as just a number. To me, it's a big mistake to explain it that way. But what J is, and I'm very confident about this because it bugged me when I was a kid, and so I really looked into this. And I want to tell you what J is. J is nothing more and nothing less. Because I'm saying we're going to nail this. What J means is a sharp turn, quarter turn, not a full circle, but a quarter full circle. J is a quarter turn to the left, a hard turn to the left. Now, you know that in your bones, and that's a good place to have knowledge. When you come to a four-way stop, and you take a hard turn to the left, you know what that means. And I'm saying J is that operation, which is a hard turn to the left. It doesn't change the magnitude, but it changes the direction. A hard turn to the left. So it's going, that's counterclockwise. 1/4 turn. 1/4 full turn. I don't want to talk about degrees or radians and all that. Those are just names. But we know what a complete turn is. You turn around and you're back to where you started. It's 1/4 of those to the left. That's J. Nothing more and nothing less. You know it in your bones, okay? You've done it hundreds and hundreds and hundreds, thousands of times when you're driving. And by the way, don't forget to look both ways, okay? So now we understand J, and I'm going to do another reminder. So discuss the meaning of the operator J. Yes, it's 1/4 turn. Oh, let me go back to that. You come to a 4-way stop, and you make a quick, sharp turn to the left, 1/4 turn. That's J. It's an operation, okay? Nothing more, nothing less. So discuss the meaning of the operator J. We did this. Wow. We're 3/4 through this presentation. We just have this last little bit that's it's so great. Just hang in there, guys and gals. So here we have, the last thing we're going to do is show geometrically the meaning of e to the j, so that you can know it in your bones. And this language, e to the j, is critical to being able to discuss waveforms and becoming at home in this modern world, which we know is quantum mechanics. Quantum mechanics describes necessarily all the functions of biology. It describes pretty much all of the functions of electronics. It turns out, and I did in my series, General Relativity 1 through 7, I did another follow-up where I broke free from the traditional classical Einstein's theories after having gone through and agreed with Einstein on all the key points with complete fidelity. I put a lot of a good basis foundation in there, and then I did a video on quantum relativity, and I didn't go into as much of the math because I need these terms. So anyway, we're going to get that next, and in a very simple kind of fashion. So let's do it, and then we'll be finished this. So here I show something very interesting. So here I show e to the 0 is equal to 1. We've been there before. And then I'm going to do e to the 0 plus j to the 0.1 is equal to e to the j 0.1, because e to the 0, see, remember I said when the exponent is, when the exponential terms multiply, the exponents add, okay? So this e to the 0 plus j to the 0.01 is kind of a small number, 0.01. It is equal to e to the 0, because the exponent, when the exponents add, the exponential terms multiply. So it's equal to e to the 0 times j to times 0.01. Now don't freak, because we already proved that e to the 0 is equal to 1. So it's just 1. And so that goes away. You multiply anything by 1 and you just get the thing, right? So it's equal to e to the j 0.01, right? So here's what I'm saying. E to the 0.01, it's a magnitude. And it's that little amount here which I'm showing in green. See that? The length of it is this term. But it's to the, and the meaning of this when I put j in there is it means it gives you the direction. J doesn't change the magnitude, but it does change the direction. It rotates the direction 1/4 full turn, 1/4 full turn to the left, okay? So e to the 0 is going along this gray line, and then we multiply it by e to the 0 plus j 0.01, which works out to this thing here. I just proved that. And so the magnitude is e to the j 0.01. You can do that on your calculator. We don't have to talk about that, but it's a small amount. And then this j gives this function here. It gives it one hard quarter full turn to the left. So we got this little magnitude, and we were going along this direction. We're going to do the same darn thing. It's because that's what j is. Around a full 1/4 turn to the left. There it is right there. This is a small amount defined by j to the 0.01. So there it is. All right. And notice that it's going along a circle. That's interesting. That is very interesting. So we're getting a g of this is notice I've got e to the 0 plus j to the 0.01, and we know it's equal to that, and then we get e to the j to the 0.01 is and we're using that now, that e to the j. We're seeing what it is, and it's a new term, and at this point your head's going to be swimming a little bit because we know what the amount of it is, the magnitude, e to the 0.01. I can look it up in my calculator. You can too. And then here it multiplied by j, which is this operation. So we know that it starts where it was along this line, and it does a sharp 1/4 turn to the left. And we did that. So there's the picture of it. And just hang in. You'll get used to it. But at least now you see it. You see what it is. Okay? Now, if you do that again, when you multiply the terms, you add the exponents. So if you took to get to j to the 0.02, it's 2 of j to the 0.01s. So you're adding 2 exponents, which means you're multiplying it. So you're doing it again. To get to e to the j 0.02. All you do is you take e to the 0 plus j to the 0.01, and you do that, you multiply it by another one of those. And then you get 2. So here, I show it. Now it's going to be operating, the second one is operating on the first, on the first deviation here, where you took and you did the, I'm going to change this back to this color here. I'm going to stick to the green now. Just hang in there for a second. It's kind of fun. There we go. Yeah, keep consistency here. So that was the first one. Then now in order to perform this function, it's equivalent to operating it on it by doing e to the j 0.01. That gives you e to the j 0.02. So I stick another one in there, and I'm doing a hard 1/4 turn to the left on this arrow, this little vector. Okay, and it gives me that little increment. Okay, so again, it's going around the circle. Oh my God. So now we do the same thing again, and now we're operating on j to the 0.02, and you get that little other line segment. And I don't have to do this in green again because you know what I'm talking about. So we'll continue on. And then what do I say here? Let's look at that, because when I put notes there, it's usually some cute little thing. So e to the 0 plus j 0.03 is equal to e to the 0 times, remember if you have times, and the j to the 0.003 is equal to j to the 0.01 plus j to the 0.01 plus j to the 0.101. Okay, so I'm going to say that again, but follow the red arrow. It'll be easier for you. E to the 0, this here is equal to e to the 0 times e to the j 0.01 plus 0.01 plus 0.01. Okay. So now that means, what that means is you do it once, e to the, and see this plus? When you see the plus in the exponents, it's multiplying the exponentials, right? So there you got the multiplications. So here's what it's saying. You start out with here's what it's equivalent to, and I draw it on the diagram, okay? E to the 0 times e to the j 0.01, okay? That's e to the 0, and then I operated on it with that exponential, and I get this line here. And then times e to the j 0.01. E to the 0.01 is the magnitude, and j is the direction, so we start with this one now, the second term, and we do that same amount. Then down here, times e to the same thing, j 0.01. So now you're operating on this vector at a 90-degree angle. You're going along that circle again, and that lasts the same increment, e to the 0.01. There is the geometrical vision of what this is doing, okay? It's going around a circle. Now you could put, for example, a time in there, and which would make it bigger and bigger and bigger and bigger, and it would go around and around and around and around this circle as time progressed. Now you're starting to see, just with that little inkling, and I haven't gotten into that yet. Now we're not going to cover that in this presentation because we've covered enough. But it gives you an idea of how you can talk about waves and those sorts of things. So now, let's see now what we can do here. Oh, I think it was it, who came up with this? I think it was Euclid. Euclid came up with something which normally I guess I'll wait till I show it to you, and then I'll talk about how we normally people derive this and compare it to what we're going to do here. Which, let me talk about it. So if I take this we just went, for example, we derived this, okay? So now we can, we can take this here, and if you look at this top blue line, the net result, and that's for e to the j 0.03. It's a picture of it right there, okay? And then we label that length AC, okay? And then we can see that that's equal to AB, this distance, and then you got to do a quarter turn, a sharp quarter turn to the quarter of a full turn to the left to get up here, right? So if you could do this vector, and then you do a sharp quarter turn for this amount, you get this vector, you get AC, okay? Now, we know that, so what we have here, I'm going to just show you, I'm going to write it algebraically here. First of all, AC equals 1. That's because it's on a circle with the radius is e to the 0 equals 1. Okay, so that's true. Now, I want to talk vectors for a second. If you look at this, AB plus BC is equal to AC. That's in vector talk, right? Okay. So I'll show you with the red arrow. AB plus BC is equal to AC, okay? Now, AB, the red arrow, divided by AC, is what we know as the opposite line. If you take it as a magnitude, okay, just a number, divided by the diagonal line, or what some people call the hypotenuse, right? So the opposite divided by the hypotenuse, somebody way back in antiquity gave it the name cosine, which is just a name. You know, in my mind, I don't use that, tell you the truth, because I want a picture. It's the opposite divided by the hypotenuse, and they call that cosine, okay? But you don't even have to call it anything. You know what it is, right? So AB over AC plus, so that's that thing. It's, you know, it's equal to cosine theta. They put this thing kind of an angle, and you can call it radians or degrees, you know, whatever. In this case, it's degrees because it doesn't follow the arc. It goes straight up. Okay, so it's degrees. And this over here, see the arc? It follows the arc. You can use radians for that. This one, we're talking now, we're going to use degrees. So AB plus BC is vectors equal to AC. It's equal to e to the j 0.03. And then we know that AB divided by AC. Now, AB is just it's like a number because it's a magnitude, and AC is a magnitude. So you divide these two, and you get what is traditionally known as cos theta by definition. Okay, just the name, but they gave it that name. Where theta is the angle in here, in degrees. Now, plus, so that's this one here. And then now you say, now AC is equal to 1 on this thing, okay? So it's just going to be equal to AB. So it's that line here, all right? Cos theta. Now if you and it's going along the real axis here. So that whatever this ratio is here is a number. You can see it on this axis down here. Now, if you take the length CB and divide it by the length AC, that's what way back in antiquity they called that ratio, which is just this length AC as a number, divided by the length AC, the magnitude, the number, and the ratio of that they call sine theta. Okay? And it's this number here, this magnitude here. It's not a direction yet. So to get it to go in the right direction, to make it add properly, you need to put this sharp right turn operator on it. Okay? J, you need to do 1/4 of one full term to the left. So you need to, see here's J. You need to, at this point, go, and do a chord. I say that to kind of get it in your brain, that you're at a four-way stop again. And you make this turn, and you go this far. That then gives you AC, right? Which is E to the J 0.03. So E to the J, some number, is equal to cos theta plus J sine theta. That's, I think Euler came up with that. And I don't know how he did it, but we're doing it very simply just by geometry, which is kind of interesting. Actually, very interesting. So now the traditional way, I remember I said I'd tell you what the traditional way is. The traditional way is you take the Taylor series expansions for e to the j, whatever, e to the j some number, in this case 0.03. You take the Taylor series expansion of that, right? And you take this Taylor series expansion of cos theta for whatever that angle is. And an angle is kind of a, 360 degrees. They give it 360 for one full term. That's arbitrary. So I don't like arbitrary things as much. But you can take the Taylor series expansion of that arbitrary thing called an angle. And with 360 degrees is arbitrary. They can divide it up into something else. And then you take the J, you have to operate on this. Sine theta just gives you a number, right? Then you have to put a J on it to give it a direction. So you take this Taylor series of that and add those two together, you get the Taylor series of E, if you find out it equals the Taylor series of E to the J, whatever the number is. And that's the traditional way of proving it. Ladies and gentlemen, let me just say that I much, much, much prefer this simple geometric solution where you know what it is and you know that it's equal to cos theta plus j sine theta right away, because you just look at the freaking diagram there. It's so simple. Once you get used to this, everything just jumps out at you all at once. You see it. I wonder if I can do this all at once. It's hard for me to snap. Took a lot of practice. Okay, so we've actually done it. We've done it. So I hope you didn't find it too long or anything. But let me, as a means of wrapping up, it's very useful to just go over what we intended to do and just ask the question: did we actually achieve it? So what we had hoped to do was to, one, develop a definition of the exponential function that does what we need it to do. So we went through and we looked at the traditional definition, and we found that it led to some logical paradoxes. And we wanted to, let's say, improve that definition so it doesn't lead to logical paradoxes. And I think we did that. Then we wanted to solve for this exponential function so that f of x equals the slope of f of x. And we found, so we did that. We found that it could be, that function could be achieved if the base was a particular number that was just shy of 3. What is it? 2.7, 218, 218, something like that. And it goes on and on and on. So we did that. We solved it for it. We know what the condition was. Then the third, we wanted to discuss the geometric meaning of the operator j. Now we did that. It's no more or no less than what you do when you come to a four-way stop and you look both ways, and you take a hard left 1/4 full turn to the left. You come to the stop, and then you take a 1/4 of 1 full turn to the left. That's what the operator j does. In this case, you're doing it to your car. Okay? So we did that. We know what j is. No more and no less. And then we showed geometrically the meaning of e to the j so that you can know it in your bones. And we did that. We showed how we get what e to the j, if you put some magnitude there, like time, for example, as time increases, it makes it go around and around and around in a circle with a constant radius equal to 1. And more than that, as a bonus, we got the Euler equation, e to the j is equal to, what was it? Cos theta plus j sine theta. It's right in the diagram, it literally jumps out at you, and we found that and we did that. So with that, let me just say I really, really enjoyed presenting this tonight to you. And with that, I wish you a very good night. Thank you very much. Bye now.